Thanks, Cedric. I think that the tea is almost finished, so that's great. Welcome, everyone. Good afternoon. My name is Tjeerd, and together with these other people on the slide, I would like to present our results on the 3D seismic characterization of one of the largest active landslides here in the Alps, which is actually only a few kilometers away from where we are. And the people that were already last year or here last week, we've done already a nice excursion. You actually see the route that we walked. So some in the room have already seen the landslide. For others, I'll try to introduce it a bit. But first about landslides and the motivation why to actually study landslides. So landslides are one of the most destructive natural hazard phenomena, which is, for example, illustrated by this rock slide last year, actually relatively close by in Brienz, but also, for example, here in Colombia very recently, or Pakistan or Afghanistan only 2 months ago, which resulted in a large number of fatalities as well. And to quickly quantify these fatalities, I found this paper from 2018, and I would like to highlight one section, which is this section, where they state that in the period from January 2004 to December 2016, their data shows that close to 56,000 people were killed in almost 5,000 distinct landslide events. And I think that this really highlights that it's crucial to characterize and monitor such unstable slopes. Now, in order to reduce the risk of such unstable slopes, they have been actively monitored, of course, often by remote sensing methods. So, for example, radar, GPS, satellites, etc. And they often provide high accuracy measurements with a wide spatial coverage. And an example of such a study was also conducted at the landslide that we are studying, so the Quam V, which is shown here, where they show the surface displacement in the color scale from 0 to 5 meters in a 15-year period. And this is great information for the risk assessment, for example, for this slope. However, such remote sensing methods cannot inspect the landslide subsurface directly. And this is exactly where geophysical methods can come into play. Try not to step on a few cables. Where geophysical methods can come into play because they can actually look inside such an instability. Now, a versatile class of such geophysical methods are the seismic methods that most of us are working on. And in this context, we often look at seismic velocity or velocity changes because those are related to mechanical properties such as rigidity, which Erik also highlighted yesterday. Now, so seismic methods have been applied before in the context of unstable slopes, for example, in a passive way to monitor rockfall, or to, for example, study subsurface changes in the days or weeks prior to such a landslide failure. They have been applied in an active sense as well to, for example, constrain 2D profiles and find the depth of, for example, the bedrock. Now, typical deployments of such seismic investigations often consisted of several tens of sensors, and that is the main difference with our project, where we try to characterize and monitor such a very large-scale landslide with very high resolution in a 3D sense. And we try to do that by employing more than 1,000 autonomous geophones or nodes, and by using fiber optic techniques such as distributed acoustic and strain sensing. Now then, what I would like to show today, so briefly highlight the project goals. Then I would like to introduce the test site, Quam V. So sorry for the people that were here last week as well, that will be a bit of a repetition. Then about the field deployment and the data set that we collected. And today I would like to show the results of the 2D and 3D tomography that we have applied to this landslide. Let's start with the project goal. Let's say the overarching goal of our project is to further develop strategies for the seismic landslide characterization and monitoring to provide new tools for the assessment and mitigation of landslide risks. Now, and we have subdivided this in, let's say, 3 sub-goals. First goal, sub-goal, really focused on the characterization of the landslide body. The second one, to monitor landslide dynamics over time, so tracking their movement and the internal parameters and changes that drive this unstable slope over time. And the third one is a bit more technical. It's more around integrating different data types, so different observables, and exploit the complementarity. And in today's talk, I would like to focus on this first part, so really the characterization of the landslide body and establishing a subsurface structural model. Now, then briefly about the Quam V landslide. So half of the room has seen this picture last week already, but then from the ground. So this is the Quam V landslide, which is one of the largest active landslides in the Alps. And it's situated, as I said, it's just around the corner, above the village of Seismic at the end of the Rhine Valley. And it has been pretty active over the past years, for example, shown by this event in 2016 on the western side of this landslide, as well as, for example, these large-scale opening crack features at the top, which accommodate a significant part of the displacement. Now, this is the same picture, but now with a map next to it, a topographic map, where from west to east at the landslide shoulder, the instability is approximately 1 kilometer wide and 1.3 kilometers long in the southwest direction. And it mainly consists of, let's say, two main parts. So you have the landslide shoulder on top and a 30-degree slope running down into the valley of Seismic, covering around 700 meters of elevation. Now, because of its instability, it has been monitored already quite a bit over the past 2 decades. For example, by these reflector poles, of which there are 8 of them, which are also shown on the map, which are connected to this laser device in the valley, which measures the displacement of those poles up to 1 millimeter accuracy every 4 hours. And if we, for example, look at the data of those 2 stations on the landslide shoulder, plot that data for the past 3 years, we obtain a plot like this with time on the x-axis and the velocity on the y-axis, where if you add up, let's say, the monthly displacements, this adds up to around 10 to 15 centimeters per year. But secondly, very interestingly, are these 3 distinct peaks, always towards the end of spring, which is probably related to the influx of the snow melt water. Now, then briefly about the field deployment and the data set that we have acquired. So this is the same map again before our field deployment. And I would like to highlight the 3 main components of our configuration at the landslide. And I would like to start with the fiber optics, where we have trenched several kilometers of fiber optic cable. So we made a trench of several kilometers crossing the entire landslide, in which we deployed a fiber optic cable and then spliced all the cable parts together. Now, and we mainly did this for the purpose of distributed acoustic sensing. Many of you have already touched on this topic, so I don't have to go into detail. But basically, by using this technique, we can convert this cable at the landslide into a distributed line of seismic sensors. And especially for the monitoring aspect, that's great because this cable can remain in the ground. It's still in the ground. It will probably also be in the ground for quite a while, and is therefore very suited for long-term monitoring of this landslide. The second technique is slightly different. It's called distributed strain sensing, which is using a slightly different technique. But that technique provides absolute strain observations along the cable and is therefore really meant to observe the strain evolution along the cable over the many years. Now, then briefly about the configuration. So we have the interrogator here at the cable car station, and then 6.5 kilometers of trenched cable at the landslide. And from 2022 till now, we have already acquired a large data set, one in the summer of 2022 and one 6-month continuous period in the spring of 2023. And actually regular data acquisition is still ongoing, mostly at the moment with DSS measurements. Now then about the nodal array, we've installed more than 1,000 of these 1-component nodes, which can run autonomously for 28 days. And the reason that we could install so many of them is because they're small and light, and therefore you can have more than 100 on your back. And we deployed those in this configuration in a few days. And so in total, this configuration consists of 1,046 of those 1-component nodes. The majority constitutes a hexagonal grid with a 28-meter spacing. And from June till July 2022, so also simultaneously with the DAS acquisition in that summer, all those nodes acquired data for 4 weeks continuously at 500 hertz. Now then the last part of the configuration, of the main configuration, are those all the controlled sources or active shots where we drilled many shot holes, 1 meter shot holes, and equipped that with small explosive charges that we detonated and generated seismic waves that were recorded along the entire array. And the configuration consists of a shot grid, as you can see here, and 2 shot lines, one crossing the landslide shoulder from east to west, and one running down the slope until the valley. And these add up in total to 163 of those shots. And those shots were recorded by all those nodes, and this is actually the input for the 2D and 3D tomography that I would like to show now. So, moving towards the tomography. So briefly about the tomography setup at QuamDaV, what we've done. So we're using an established technique called travel time tomography, which aims to minimize the misfit between the observed and predicted data. And in our case, the observed data are 26,000 first arrival pics from all those shots and receivers. And this is then the input for a 2D and 3D array-based solver. Now there are 2 domains, 2 tomography domains that we've worked on. The first of all is a 2D profile along the entire slope based on the southwest-northeast shot line. And the other domain is a 3D model here at the landslide shoulder, including all the shots and receivers at this part of the landslide shoulder. And I would like to start with the 2D profile along the slope. So if we run the inversion process for this data, we obtain this profile with depth on the y-axis and the lateral distance on the x-axis, where on the left side of the profile this is the toe of the landslide here in the southwest, and on the right side is the shoulder part here in the northeast. And in the color scale, these colors range from approximately 800 meters per second, so very damaged and fractured rock, up till, for example, let's say 3,500 meters, which is more intact. If we look at the profile, the main feature that stands out is this clear low velocity body. And we can compare this with actually surface displacement measurements done at this landslide, where in very light gray we have the region which is almost stable, moving only up to 6 centimeters per year, towards darker gray colors, which indicate velocities up to 12 to 18 centimeters per year. And if you now look at the lateral extent of this low velocity body at this place, and we put that position in a map, it plots approximately at this position, which is indeed the area where we expect to move from, that's a stable grounds in the southwest towards towards unstable subsurface in the northeast. But more interestingly, something that this map of course doesn't show is if we look at the features in depth. So for example, if we look at this position at, let's say, the bottom part of the low velocity body, we see at approximately 100 meters depth, we see a very sharp transition from low velocities in the order of 1,000 meters per second to much higher velocities in the range of 3,500 meters per second. So there's a very sharp transition at this point from highly damaged rock to much more intact rock. Now moving a bit more to the northeast, such a transition is less clear, but this is exactly this area where we have our 3D tomography model. And I would like to move to there now. So this is the domain again of our 3D velocity model at the landslide shoulder. And I would like to go through the model from top to bottom, so going through the different depth slices. And I would like to start relatively shallowly, or at a shallow level, at approximately 20 to 25 meters below the surface, where I only plot the model which is resolved, so the darker or black part around. It's unresolved because it's not sufficiently covered by rays. And if you look at the resolved model, you already see clear lateral changes. So for example, lower velocities in this area, where those velocities match also the velocities of the 2D profile, which crosses at this point. And in addition, this is also the area where from surface displacement measurements we know that this area is moving the fastest, which could explain the more damage and therefore lower velocities in this area. And for example, a bit more to the northeast, in this area we observe clearly higher velocities instead of, let's say, 800 more towards 1500 meters per second. And if we zoom in a bit further on this area, we can plot a map of all mapped geomorphological features, so cracks, faults, ruptures, etc. And we see that in this area, the landslide, as expected, of course, it's one big mess, you could say, with different types of fault structures, cracks, etc. However, if we look at this area with higher velocities, and we plot the same location in the geomorphological map, it's exactly at this spot where, also from a geomorphological point of view, we observe less faults, cracks, and ruptures that cross this area, which could explain, let's say, less damage and therefore higher velocities in this area. Now then we can go deeper to deeper levels in the model, so we move deeper, 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 deeper. And I would like to stop again at 100 meters depth, where we observe that actually this area, which previously contained relatively higher velocities, has now transitioned into actually an area with relatively lower velocities. But something that I would like to highlight is especially this area, where you observe significantly higher velocities. And if we look at an aerial picture of this area, we observe this, which is an aerial picture of that area, which is dominated by these two large crack features of approximately 80 to 100 meters long and 10 to 20 meters wide, which separates a more stable area in the northeast from unstable grounds in the southwest. And if we plot the location of those cracks in our velocity model, they plot at this spot, which would suggest that these crack features propagate to at least 100 meters, to at least 100 meters depth, where they would still separate higher velocities, so more intact and stable subsurface in the northeast, from more damaged and unstable parts in the southwest. And then we can go deeper, deeper, deeper to, for example, 160 meters depth, where we still observe clear lateral changes. For example, this lower velocity area compared to these higher velocity zones. And this, we're actually currently in the process of discussing and further interpretation of these higher or these lateral velocity changes. And with that, I would like to move to some take-home messages and maybe also an outlook, where we see that by using travel time tomography, by using such a large array, we can obtain a high-resolution 2D and 3D velocity model of such a large-scale active landslide that can provide important structural information up to 150 or 200 meters depth, and that therefore such a method can be a very valuable tool for the characterization of large-scale landslides. Now, next steps. The next step would be to integrate what we have with more existing knowledge and thereby extend the interpretation. And importantly, what I would like to highlight is that this velocity model is or will be the basis for ongoing and next steps. So for example, monitoring and localizing microseismicity, with which we already started during my secondment last year at ESR. Using a match field processing approach and having promising first results there, but then decided that for continuation and also the interpretation of the results that came out of there, a velocity model could be of very high value, and therefore decided to first construct this velocity model. But with this velocity model, we could definitely continue with this. And secondly, important, we want to move more to the monitoring side of the project, so this second sub-goal that I defined earlier, towards detecting subsurface changes over time. So currently we have 2 master projects ongoing that are looking into the ambient noise data, computing cross-correlations over time, and this is something that we would like to further explore in the coming months. And with that, I would like to thank you for your attention.